All right, well, let's go ahead and get started on a few more examples so that we can continue our discussion of integration by substitution. In the last video, we did several examples that were basically polynomial and a couple of trig ones. I'd like to sort of branch out and do a couple from different classes of functions. So the next one we're going to do is we're going to do a rational one. Okay. I'm going to do two rational ones, and then we'll probably move on to some exponential. Okay. Now, that right there, we run into a bit of a problem. Okay. The problem here is that if it were x squared plus 2 over x, meaning the reciprocal of what we're given right here, it'd be very, very easy, right? It had monomial denominator, we'd split it apart, and we go term by term. This, however, when it's in a rational form, we have several different possibilities. We saw several different things. That wound up as rational expressions upon differentiation, right? And since I need to identify this as a particular derivative, I need to run through those possibilities. What are the types of things that have rational expressions as their derivatives? Well, we just covered one of them. Obviously, you can get a rational expression when you're dealing with polynomials. Once you start getting negative exponents, basically, obviously, those flip over, and you can combine those into a single rational expression. That's probably not going to be what's happening here because, like I said, this does not have a monomial denominator. The next thing we need to consider is the fact that this could be logarithmic, right? The derivative of natural log x is 1 over x, okay? So this could be a little bit more complicated chain rule version of a natural log derivative. Or this could be inverse trig, okay? Well, let's go ahead and let's assume that it's natural log, okay? Now, if it's natural log, then the inside, okay, my candidate for u is the whole denominator, okay? And let's see whether that works, right? Because remember that when I'm dealing with undoing derivatives, if I have the derivative of natural log u, which would be our chain rule version of that differentiation rule, right? It would be u prime over u, right? The inside, or what we usually term in terms of a composite function, my g of x, right, is my argument of the logarithm. And that's what winds up in the denominator. So if I want to undo it, I know to go from here to here, to go from the rational expression back to the logarithm, I need to see whether that denominator is indeed my u and will therefore be the argument of my logarithm upon executing successfully the integral that I'm given. So if u is equal to x squared plus 2, then du is 2x dx. Now, do I have all the pieces that I need? And the answer is yes, okay? The only thing that needs to be supplied is I need a 2 in there. And of course, if I put a 2 in there, I need to numerically cancel it out by putting the 1/2 out in front, lest I change the value. And so I have 1/2. And of course, the only thing that needs to be done here in order to group them is, remember, you just need to sort of ship that up. And just notationally, you can pop that up into the numerator. It being in the numerator and it being multiplied by that rational expression are exactly the same thing. And so 2x dx is my du, and I have u right there, okay? So I have 1/2 natural log the absolute value of u plus c. But of course, once I resubstitute, I recognize the fact that I don't need those absolute value bars because x squared plus 2 is an expression that will never be 0 or negative. It's always going to be positive. And therefore, I have successfully identified that rational integrand as the derivative of a natural log function, and therefore I was capable of undoing it. Now, let's go ahead and look at one that's a little bit similar. Let's look at x over x to the 4th plus 1 dx. Well, here's the thing. if I look at that and I go, well, I want to determine whether that is a natural log integral, I make u equal to the whole denominator, and then I wind up getting du is equal to 4x cubed dx. Okay, I have a problem here. I have 1x, but I don't have the other 2 that this requires. So that must not be it. Okay. Now if it's not going to be term by term undoing of power rule, and it's not natural log, chances are that this is inverse trig. Now there's only one inverse trig, or two if you count their cofunctions. There's only one that is without a radical in the denominator, and that's arctan, right? So, and I know that arctan requires that it be something squared plus 1, but I can rewrite x to the fourth as, x squared squared, right? Plus 1 with an x up there. We'll go ahead and put the dx up there just for good measure. Now, if I'm dealing with arctan, the inside, my candidate for u is not the whole denominator, it's whatever's being squared right here, right? Because if I'm dealing with the derivative of arctan u, remember that that winds up being u prime over u squared plus 1. Okay, so the inside, the g of x, the inside of the composite function, is what winds up being squared right here. Okay, well that makes my candidate for u x squared, and my du 2x dx. Well, that actually works because I can put a 2 right there, pop a 1/2 out in front, and all of a sudden I have 1/2 du over u squared plus 1, and that is going to integrate very, very easily into 1/2 inverse tangent u plus c, or 1/2 inverse tangent of x squared plus c. Okay. Now I usually put arctan, but I didn't want to run off the end of the paper, so I was just trying to save space by using the inverse tangent right there. But that is basically what you need to do when you encounter an integrand that is rational. Okay. Well, let's go ahead and see if we can actually get to a few more that are a little bit more, that are of different classes, right? We want to make sure that we cover everything. So let's go ahead and let's look at, how about e to the x squared plus x, and you have, okay. Now, of course, that's a really easy one, but since sometimes exponentials wind up being a little bit difficult for us, I thought I'd start out with a relatively easy one. Now, obviously, when you're dealing with differentiating exponentials like e to the u, you know that e to the u times u prime, right? The inside is the exponent. Okay, so my candidate, when I'm looking at an exponential, my candidate for u is either the whole exponential or the exponent, most often just the exponent. So I want to basically make it x squared plus x. I know that du is 2x plus 1 dx. That makes it very, very easy to transform this into e to the u du, which is e to the u plus c. And when I resubstitute my x expression back in, I get that. Okay. Now, the ones that we have done so far have been relatively straightforward. There are, however, ones that get a little bit sticky, and after this next one, we're actually going to get to one that's a little bit sticky. Let's say we have the integral of 2 sine x cosine x dx. Okay. Now it's an exponential again. The bummer is the fact that it's not it's not e, it's base 2. Okay. Now remember that when we were dealing with the derivative of a to the u instead of e to the u, you had a to the u times natural log a times u prime. Okay, so we are going to have to provide that as well as making sure that we have the u prime in order for my integrand to be complete and therefore for the integral to be capable of being integrated. So what we're going to do is we're going to go ahead and identify u as that exponent. It works out because du winds up being cosine x dx, okay? But when I get to here and I recognize that it's 2 to the u du, I recognize that I also am going to need natural log 2, which means I need to divide by natural log 2, such that when I integrate, I get 1 over natural log 2 times 2 to the u plus c, or 1 over natural log 2 times 2 to the sine x plus c. And that, right there, is your integral. Now, like I said, these have been relatively straightforward. Some, however, are not. Okay? And I'm going to go through two examples right now that are very, very similar to one another, and they're hard to see. Now, if I were to give you natural log x over x dx, what's my u value? See, here's the hard part, because this is a combination function of two different classes, okay? Now, if I were to give you natural log x squared, you probably would have seen the right answer, because there would have been parentheses there, and you would have probably gone, okay, well that probably is written like this, a little bit better. My u is what's in the parentheses. My du is 1 over x dx, and therefore this becomes u squared du. But I didn't give you it in the parentheses, I gave you that. Well, is it any less, let's put it that way, is it any less legitimate to do it this way and to think of it as natural log x to the first? And no, and that's exactly how you need to think about it, because this one as well, it is still u being my natural log x. My du is still 1 over x dx, and so this winds up being u du. It looked really nasty right here, but the moment that you identified the correct u, that cleans up very, very nicely. Okay, and so it winds up being 1/2 u squared plus c, or 1/2 natural log x squared plus c. And of course, I think I've told you this before, some people just like dealing with trigonometric functions to powers sometimes put, instead of the parentheses, they have a lazy man's version of the of squaring or raising a natural log or a regular logarithmic function to a power. They put it right there so that you know it's not the argument that's being squared, but the whole function that's being squared. So either one of those is legitimate notation. Okay, well, how about one that's similar? Okay? How about this? And of course, this one's going to be pretty easy for you since I just did the previous one. So you have arctan x squared plus 1. Well, like I said before, if I had put parentheses around the arctan and raised it to the second power, or raised it to whatever power, it would have been very easy to see. Or perhaps if I had actually written it like this, it would have been easy to see, okay? But either way, your u is your arctan x. Your du is your 1 over x squared plus 1 dx. So that's u du. Very, very easy. Excuse me. And we have that. And then it's 1/2 arctan x squared plus c. And that is how you would identify your u and therefore execute that integral by u substitution. We're getting on towards 15 minutes, and I like to keep these videos a little bit shorter so that they're easier to upload and stuff like that. I'm going to go ahead and call this one quits. There will be a couple more on u substitution. I want to give you as much of a wide selection of problems as I can in order to make sure that you're properly prepared for whatever quiz or test is coming up. But if you have any questions, as always, please do email me. Bye.